we're going to look at a special derivative called the directional derivative, and also a concept called the gradient, or the gradient field of a function. Now, these are things that are really core to this course. So, I think there's a good chance we'll test you on these things, and also you'll be able to use these things in other areas of maths or applied science and things like this. So, in the previous lecture, actually a few lectures ago, we defined a new type of derivative called a partial derivative. And I said that was one way of extending the idea of a derivative for functions of one variable. The directional derivative is another way of extending the concept of a derivative. So here's the definition, and they're actually extensions of the ideas of partial derivatives. Now, suppose we have, say, a function of two variables, f and some point of interest, and some unit vector. Now, wherever you see a u in this section or subsection, think of it as a unit vector. In the print version, you don't have the little hat, which tells you straight away it's a unit vector, so I've just written it in. Now, so suppose we have a function, a point, and a vector, unit vector. We can speak of the derivative of f at the point p0 in the direction of this vector. Well, it's just the following limit, if the limit exists. Let's analyse this because it's a bit abstract. It looks a little bit like partial derivatives. But there's a difference. You're making changes in potentially both the variables of f, not just one or the other. So what I like to do when I'm confronted with something that looks a little bit confusing, I like to look at special cases. So let's choose a real special case. So let's choose some unit vector to be just the vector I. That's a unit vector, and it's got a particular direction. Can anyone tell me what our directional derivative will be in the case when the unit vector is just the vector 1, 0? What will the df ds at any point be? Well, all we have to do is put u1 equals 1 in there and u2 equals 0 in there. What's that special limit? Anyone remember? Oh, someone sort of said it. Yeah, it's the partial derivative of f with respect to x. At the point of interest. Okay, so what we're seeing on this slide is actually just a generalisation of what we already know. So it's nothing to be upset about or worried about. You can break it down to a partial derivative in the case when the unit vector is just the I vector. Similarly, what do you think when the unit vector is going to be j? If the unit vector is j? Well, in that case, the partial derivative will be with respect to y at the point of interest. Okay, so there are two special cases that you've already seen. Now, the beauty of the directional derivative is that you're not confined to directions just with these two vectors. You can take a combination of these two vectors and look at the derivative in other directions. So that's what we're going to look at today, or at least in the first half of this lecture. So the directional derivative is like a partial derivative, but you can look at different directions, not just sort of directions where the vertical planes are parallel to the certain coordinate planes. Okay. Now let's think about the geometric interpretation. What does this limit actually mean? Well, I'll discuss that in a minute. There is a little bit of a few pictures here. I'm not actually going to talk about that. I'm going to get to this, because I think actually this is the best way of explaining it, and then relate it back to the previous slide. All right, the blue is the surface associated with the function of f equals x comma y, function of two variables. You have got a point of interest in the domain P0 of your function f. At that point, you can place the tail of this vector, which is a given vector, in the xy plane. It's going to point in some direction, this unit vector. Now, if you go straight up from the point P0, you're going to touch the surface at one point. So if you can combine this vector here and this vector here, they're going to span this sort of pinky, orangey plane. So they'll lie in a plane. Now note that this plane, at least in this picture, is not parallel to either of the coordinate axes. Not like it was with partial derivatives. Okay, so you've got this plane, this vertical plane. Just like partial derivatives, it's going to intersect the blue surface along this blue curve. Now, that blue curve will have a tangent line associated with it. In the limit, the directional derivative at the point P0 is just the slope of that tangent line. So the directional derivative agrees with what you already know, your idea of a derivative. It's a slope of a tangent line, but this is a special tangent line. Okay? It lies in a special plane that is constructed, again, once you know this point and this vector, and of course your f, because then you can get that blue point up here. Okay, so it's not a huge leap from what you already know. Directional derivative is just the slope of a tangent line in a special plane, that lies in a special plane. Okay? Now, just a little bit of notation. Sometimes they have this, notation here, Dorf. Sometimes I actually write it like this. Okay? You can put a subscript to say that you're evaluating it at P, like they have here in the printed notes, or you can just put Dorf of P sub naught. Okay, so let's just put that into words. The rate of change of f in the direction of the unit vector u is the slope of the tangent line to this curve C at this P point up here. Okay, so it's just the slope of a tangent line. That's all it is. Now, of course, these things are hard to visualise sometimes because you're really trying to work in 3 dimensions. Okay, but I hope that you can get some idea of what we're calculating from that picture. That's probably the best way I can explain it, just by using this picture. Okay, slope of a tangent line in a special plane. That's it. Now, just like regular derivatives, we don't always use limits to actually calculate them. And it's the same with the directional derivative. There's more efficient ways of computing them than by evaluating limits. the computational device that we're going to use involves a new concept called the gradient, or the gradient field of a function of two variables. So we're going to explore that and see how you can use it to compute a directional derivative. Okay, well, I guess if we have some function of two variables and some point p0, we define the gradient vector, or just the gradient, of f at p0 to be this. I guess technically what we're doing is first computing these derivatives and then evaluating them at the point of interest. Now, note that we start with some real valued function, f of x comma y, and we're producing a vector. So you take a scalar valued function, and this gradient operator produces a vector, or a so-called vector field. This is very important. Okay, so you're producing a vector just with the partial derivatives as the components. All right, so let's do a simple example and see how it works. If this is our function of two variables, calculate the gradient of f, just generally, and also the gradient of f at this point. Now, when we use, I guess if we use slang, I don't want to always say the gradient of f, so I say grad f, okay, or nabla f. But grad f is more common. Who's studying physics here? Anybody heard of a gradient field? You have, good. Okay, you guys will see a lot more of it in physics if you do second and third year physics. All right, so let's look at it. By definition, now note that I'm putting a little tilde under my nabla. That's to emphasize that I'm dealing with a vector here, or a vector field. Okay, you don't see it there, but you see it there. It helps me keep track of things. So let's calculate the partials. So differentiate with respect to x, 3x squared, differentiate with respect to y. And I get that. And so the gradient at the point 1, 2, I just take my x value, sub it in there, and my y value, sub it in, and I get this. Okay, pretty easy. All you've got to do is calculate the partials, write them as a vector. That's it. Okay, so how does this actually relate back to this directional derivative? Well, the directional derivative is a dot product. A dot product, so the directional derivative at a point, p0, is a dot product of the grad f at p0 dotted with the unit vector u. Now I'm not going to prove that, but you can take that as a given. I don't have time to prove it today, but it's, I'll prove some other stuff. But this is great because you don't have to worry about calculating limits. Okay, all you have to do is take a dot product. It's pretty good. It's pretty convenient from a computational point of view. That's excellent. All right, so I guess this sort of subsection is all about functions of two variables. We'll talk about functions of three variables in a minute. Okay, you can talk about the gradient of f where f depends on three things or four things or whatever. Okay. Now I know the font is a little bit small here, so I apologise for that. Here's one I prepared earlier. I've got a function of two variables, a point of interest which is 2, 0, and I want to find the directional derivative of this function in this direction. Now, remember, when we use this, we're dealing with a unit vector. So the first task is to see, well, if we're working in this direction, is this a unit vector? If it's not, we can make it one. Okay? So to apply our dot product formula, I have to first of all construct or recognise whether or not we've got a unit vector. So here I don't have a unit vector, but all I need to do is calculate the magnitude or the length, and then this is then a unit vector. Okay, what else do I need? I need my gradient. So what I do is I calculate the two partials at the point, and then I'll get this. Okay, by this figure I mean the figure down here. Okay, so using the Duff notation, our directional derivative is just the dot product of the gradient with the unit vector. So I calculate that and I come up with a value. Now let's think about it. What does this value mean? I've got -1. Let's try to interpret the answer. Can anybody sort of have a guess at what the surface might be doing if I stand at that point and look in the direction of the unit vector, or the vector v, say? We've got a negative answer. Can anyone sort of have a guess at what the surface might be doing in that direction? Yeah, who said that? Yes, right, because the derivative's negative. Okay? So that's one sort of insight. Now, these are pretty easy problems, okay? We expect you to, like they're very low on the difficulty scale because it's just a computational exercise. Can you take a partial derivative? Can you produce a unit vector given another vector? Okay? Let's have a look at some geometric significance. In this picture, we've drawn some of the level curves of f. So these blue lines are various level curves of f. Here's our point of interest. And at that point, I've put in the vector grad f. Now, if I draw a tangent to the level curves, can anyone conjecture what the relationship between the gradient vector and the tangent might be? Yeah, it sort of looks, at least from what I've drawn, that they might be sort of perpendicular to each other. Now, I haven't proved that, but that's one important geometric property that if we've got time, we'll prove it. Okay? Now, what else does this most excellent formula, computational formula, allow us to do? Well, the dot product can be expressed in terms of the angle between the two vectors, right? So we can use that to our advantage. Let me show you how. If theta is the angle between the directional vector and the gradient vector, then because we can write the directional derivative in terms of a dot product, we can make the following conclusions about directions of maximum increase, maximum decrease, and direction of no change in f. Now, I know this is slightly confusing. By these, of course, I mean the magnitude of these vectors. Okay, I've just put one here and one here just to be consistent, at least on this page. Okay. All right. Well, let's look at it. We know that because this is a unit vector, it's got length 1. So we also know that cosine theta varies between -1 and 1. Okay. Now, the directional derivative is going to be a maximum when cosine theta equals 1. So let's think, when does cosine theta equals 1? For what value of theta? 0. Okay, so based on that, the directional derivative and the vector u, if they point in the same direction, then the f is going to have the maximum, f's going to have the maximum value. Okay? And the actual directional derivative is just this, because this is 1, right? So you get, this becomes this. Now, let's think about where cosine theta is -1. Well, when does that happen? When theta's pi, right? So if the gradient vector points that way and the u points the opposite way, right? The direction of most rapid decrease is going to be in this direction. And again, at that, the directional derivative is going to just be negative, the magnitude of delta f. Now let's think about where cosine theta is 0, because that will represent a 0 change in f. Well, that's when theta equals pi on 2. So you're going to have an angle of, I guess the two vectors involved are going to be orthogonal then. So we're going to use those three important facts that you have to recall. Okay, we won't give them to you in the exam. You'll need to recall those. You can probably derive them if you forget them anyway. Before we get to that, though, a good question here is, why do we use a unit vector? Why don't we just use any old vector in our definition of directional derivative? Anyone know? Well, I guess the bottom line sort of sums it up. If we use a unit vector, then we can talk about the rate of change per unit change in the direction of u hat, per unit change. If it wasn't a unit vector, then we could talk about, the rate of change of f per 2 unit change. Okay, something like that. Anyway, let's look at another example. I'll come back to this a bit later, but let me just summarise, if I've got time. The gradient vector of a function f is actually normal to the level curves of f. Okay, so I've sort of drawn it up somewhere there. Think of this as a curve. Okay, we can parameterize it using some sort of vector function. Because it's f's equal to a constant, you can talk about this. Okay, so because f equals a constant on here, basically I start with this equation and then I differentiate, and using the chain rule, I can show the following. Okay, this is just and if I differentiate a constant, I just get 0. So if the dot product of two vectors is 0, we know that they've got to be perpendicular. Okay, it's kind of cute. Yes? K. Because f equals k, a constant. You with me? R of t. Okay, so we can, parameterize this curve at this point, say r equals r of t naught equals the, You with me? So parameterize the curve, look at the tangent vector, show that the gradient and the tangent vector are orthogonal. Okay, so you can move from here to here. If you're worried about how I got from here to here, well, it's just the chain rule. And the nice thing about this is that it's written in a real compact form. You can go back and verify it, but we'll also look at it in a minute. Anyway, let's do an example. Okay, this is a standard level, I would think. Here I've got a surface, actually a paraboloid, some point, 1, 1. We are asked to determine the directions in which our function increases most rapidly, decreases most rapidly, and has 0 change. So, essentially it's just an application of these 3 points. So, the first one, just calculate the gradient vector, and that's the direction of greatest change. For the second one, the direction of most rapid decrease is in the opposite direction to this vector, so you just put a negative sign around it. Okay? And then the third one's a little bit trickier, so I'll show you how to do that in a second. So, so let's look at this gradient. Let's calculate it. I guess, hang on, P. Yep. So let's calculate the partial derivatives. So we're going to get x comma y at 1, 1, which is just 1, 1. Doesn't have to be a unit vector. Okay. In fact, maybe I'll change that to a v just to not confuse you. So part 2 is just the opposite direction. So let's change that to a v2. Let's say w. So we just change the signs on that, -1, -1. So they're pretty easy, right? Now, it's a little bit more subtle when you want to work out the direction of 0 change. It's a little bit more subtle. Okay. So if, say, let's say Z is our direction, what we want to do is dot Z with grad F at P. Okay? So Z1, Z2 dotted with 1, 1. So we want to solve Z1 plus Z2 equals 0. So now all we have to do is pick a suitable Z1 and Z2. So whatever Z1 is, choose Z2 to be negative, right? So -1. So our vectors then are 1, -1, and -1, 1. So you can see those two vectors here and here. Okay, there's the vector we calculated first, there's the second vector, and these are the two vectors we calculated in the third case. So they're pretty standard questions. Obviously the third one's a little bit more difficult than the other two. The other two are really pretty easy. Okay. A pseudo applied problem. We've got a temperature function here. And we're asked to determine the direction of maximum decrease at a particular point. So very similar to part 2 of the previous problem. T. Okay, so let's calculate that, and we've got so what are we going to get? We're going to get 3x squared minus 3y squared minus 6xy at 1, 2. Is that looking good? Yeah? Have I done those derivatives properly? Okay, so all I need to do now is sub in these numbers. So 3 minus 12, and we're going to get minus 12 in there, so that'll give us minus 9, 9, 12. Okay, not too bad. Very computational. So even if you forget this in the exam, you can derive it just by looking at the dot product. Okay, look at the angle. Now that's functions of two variables. it's very easy to extend the idea to functions of 3 variables and further. Okay, you just add another component onto your vector. Okay? Once again, note that this is a vector, whereas this is real valued. It spits out a real number. So again, you can talk about gradient fields in the following sense. Okay, simple example. Here's a function of 3 variables. Let's calculate grad f. Okay, differentiate partially and write them all as components. So at our point of interest, it's going to be 3, 1, 6. Again, really easy. We've computed a vector field in the first case and a specific vector associated with the vector field in the second case. That's all it is. That's all it is. Now, where are you going to see that you might think, okay, well, that's very pretty, Chris, but what is it useful for? I'm glad you asked. Again, later on in this course, actually in the second half, you'll compute line integrals. So you'll be integrating over curves and lines. There's a fundamental theorem of calculus associated with those special integrations, and it involves gradient fields. So it's really important that you get the hang of these things now, so by the time the second half of the semester comes around, you can just compute them like that. Okay, really important, really important. Okay, calculate the direction. When we say derivative here, we mean directional derivative of this function at this point in this direction. Okay, so nothing super special about this example. Again, we use the dot product. So doof is just the dot product of these 2 vectors. Of course, dot product makes sense when we have sort of vectors in 3 dimensions, no problem. So let's compute the components. Firstly, is this a unit vector? Is it? No, it's not. Okay, so let's compute it. So you square the components and add them in square root and then divide. Now, according to my calculations, you should get 1 on root 49 here. So it's just the following. Now, come exam time, I'm always staggered at how many people can't do that bit. You can do it. You can do it. Okay? I get upset, depressed when people can't do that. Anyway, let's calculate the gradient, grad f. So it's just partials. So we're going to get 3x squared minus y squared minus 2xy and minus 1. So the gradient vector at our point of interest, just sub in. What are we going to get? We're going to get something like 3 minus 1 minus 2 and minus 1. Okay, so let's use this and dotted with okay, so just a dot product. I'm just going to bring the 1/7 out the front. So we get 4 plus 6 minus 6. 4/7. Okay. Again, pretty standard example. Pretty, it might be worth a couple of marks. No more. Just a couple of marks. Okay, now, I said earlier in the lecture that this gradient and this directional derivative can be kind of thought of as derivatives, more general derivatives. Okay? So if these, let's say if the gradient is going to be thought of as a derivative, it's good to have a calculus associated with it, right? So if the gradient is like a derivative, here's some basic algebraic rules for computing, say, gradients of product of functions, sums of functions, quotients of functions. Well, they're what you would expect. Okay? They're what you would expect. But remember, grad f, nabla f, is a vector. Grad g, nabla g, is a vector. It's really important that you can get to the level where you can look at 1 to 5 and go, right, that's going to be a vector, that's going to be a scalar, that's going to be a vector, that's going to be a scalar. That's a vector, that's not. That's real valued, that's a vector. Okay? You want to be able, because I'm amazed at how many people go through this course and don't really understand the difference between a vector and a scalar. In the first lecture of this course, I tried to make it really clear that you need to be able to distinguish between vectors and scalars. Can you see what I mean now? Some of these are vectors and some of them are scalars. Which one's which? That's very important. Okay, chain rule involved in the gradient. And in fact, I used this a couple of pages before. A good exercise is to compare this with the chain rule that we learnt in the previous lecture. Now, maybe you've worked it out, but these are just sort of this is a compact way of writing a derivative, a partial derivative. That's just, the partial derivatives are components of a vector. Okay, so that bottom line there is actually a real compact way of writing the chain, those really involved chain rules we saw in the previous lectures. All right. But this is a good slide because it shows you some of the applications. Okay, we've got a contour map of the West Point area in New York. You can see the Hudson River flowing down. And there's a little blue stream in here. I hope you can see it. That's flowing down into the Hudson. Now, think of these lines here as like level curves or contour curves. If you look closely at the map, it appears that the little tributary, it's running at normal or perpendicular to all these level curves. Anyone know why? Sorry? Who said that? Yes, can you speak up? It's going down, yeah. Why doesn't it choose another path though? Yes. Right, so as long as there's no big obstacles, water will find the quickest route to the fastest sort of path of descent to this river. And as we saw, that is actually the normal to the level curves. Normal to the level curves. So it kind of agrees with the mathematics. The intuition and the reality, I guess, kind of agrees with the mathematics that we've seen today. So assuming there's like, not a dam in the way or something. Now let's move on to some nice sort of uses of this gradient field, grad f, or nabla f. Now, for functions of, I guess for surfaces, so here's a function of 3 variables here. We can get a surface, just think of it as a level surface, one particular level surface of f of x comma y comma z. That's the blue sort of set of points. If f depends on 3 variables, then the gradient, grad f, gives you a vector that's normal to that blue surface in that picture. So this is like a natural generalization. You know how in the before I said for functions of 2 variables, the grad f's normal to the level curves? Well, this is just the same idea, beefed up a bit, where f depends on 3 things, not 2. Okay? So essentially, if you're working within this blue surface and you have any sort of smooth curve, right, let's say I've got 2 smooth curves represented by these lines. I can produce 2 tangent vectors. Right? That's what the v1 and the v2 vectors are. They're just tangent vectors to those 2 curves. Now, once I have 2 vectors, as long as they're not parallel or 0, right, I've got a plane. And from that picture, you could reasonably conclude that those 2 vectors lie in a special plane. A special plane that we call the tangent plane. Okay, so 2 important things. When we have a surface generated by this type of equation, you can always produce a normal vector to the surface just by calculating the gradient of f, the grad f. That's important. That's stuff you can use. Okay? And secondly, we're going to look at this tangent plane a little bit more closely. Okay? For example, once you have a normal vector and say a point, the point where it's touching the surface, well, you can generate the equation for the tangent plane. So I'm not going to prove this, but it's very similar to the case where we had the level curves and we showed that, I sketched the proof that the gradient was normal to those curves. Now, I did say that one of the nice things about grad f is that it allows you to simplify notation, really compact it down, so you don't have to write out partial derivatives all the time. So, these are 2 important pieces of information. Suppose I have a surface generated by this function and some point P0. We can calculate the tangent plane to that surface at this point by looking at this equation. But let's boil that down. Remember, for the equation of a tangent plane, think back to algebra, first year algebra, right? What do you need for the equation of a tangent plane? Well, you can do it a few ways. If you have a normal vector and a vector in the plane, then that's all you really need. Okay? Here's your normal vector, right? Oh. And this will be a vector in the plane. If you think in those simple terms, it's very easy to come up with these equations. Secondly, what we call a normal line to the surface at a point. So I'll actually just show you on a picture what that is. Okay? Think of this, here's our point of interest for a particular example. The normal line is this one that's sort of normal to the tangent plane that goes through the line. Well, you can write it out in a component-wise fashion like this. What do we need for a line? We'd like a point on the line and a vector parallel to the line. That's how we get the equation for a line. Well, here's your point on the line, and here's your vector parallel to the line. Okay, it's parallel because it's normal to the surface, and you want a normal line. So, for my money, this is a really good illustration of how the gradient, or grad f, can save you a lot of time. You don't have to worry about writing out all these partials and, trying to memorise stuff. I quite like it, I've got to say. Let's P naught. Okay. Let's do an example. This is a pretty simple example, but it's a reasonable example. Okay, test the basics. Here we've got a tangent. We want to calculate the tangent plane and the normal line to the surface associated with this at this point. Okay, so this surface is going to be some sort of, I guess, paraboloid, upside down paraboloid. So if you want to see a picture, here it is here. Okay, so the blue, of course, is the surface. Let's use the gradient vector or the gradient field to produce these tangent planes and normal line equations. Okay, we'll come back to that. So our x0, y0, and z0 points are just here. So, which equation we're going to use the gradient. So let's calculate it and evaluate it at the point. So if f's defined by this, then my gradient field is just a vector with the components of partial derivatives. Okay, so let's calculate those. What are they going to be? They're going to be 2x, 2y, and 1. And then let's evaluate it at the actual point of interest. So x equals 1, y equals 2, z equals 4 here, so we just substitute in. So that bottom line is the vector that's normal to our surface at the point P sub naught. Now remember, you can have two normal vectors. They can sort of point in opposite directions. Okay, so let's actually use this to calculate our equations. So at P naught, the equation of the tangent plane will be the following. So all I have to do now is sub in and take the dot product. So it's going to be 2, 4, 1 dotted with x minus 1, y minus 2, z minus 4. Okay, so the dot product, just expand it out, and then you'll have your equation. Okay, so it's going to be 2x minus 1 plus 4, y minus 2 plus 1, z minus 4 equals 0. Now, I know, you might think of it as being lazy, leaving it in that form. If you want to simplify it, you can. If you have time, that's great. If you don't simplify it, I don't think I'll penalise you, okay? Because it's much easier to read off that and mark it than if you've simplified it, I guess, in one sense. Okay, so if you want to simplify it, please do so. But I don't think it's necessary. Okay, what about the equation of the normal line at the point P sub naught? So here I've written down the vector parameterized form. T is the parameter here, and all I need to do is write down the specific details. 241. That's it. Pretty easy, right? Pretty easy. Nice and streamlined, in my opinion. Okay, so the gradient can really simplify and compact notation and, in my opinion, calculations. Sorry?
Is it okay if you write the coordinates vertically, like on top of each other?
Oh, sure. If you want to write it as a column, say a column vector, no problem. I'm just doing that here to save a bit of space. Yeah. Any other questions? Okay. So here's, like I said, here's the picture, here's the tangent plane, here's the normal line. Okay, another nice use of the directional derivative is in the area of, I guess that they still call it gradient, but sort of, I guess, gradients possibly in another sense. Suppose we've got a surface represented by the graph of f. Okay, it's a surface of, say it's a surface of a mountain, and it lies above the xy plane. Now, the directional derivative in the, and again, these are unit vectors, right? In the direction of this unit vector, well, we can draw a little triangle. Okay, so basically just move this vector up here. So you've got a point touching, right? And just draw it again, parallel to the xy plane, right? You can form this tangent vector W, and this length will be the directional derivative. Remember, that's just a number. Now, if you just look at basic, from your right angle triangle, just look at your basic trig, then the tan of this angle, phi, is just the directional derivative. Okay, so let me put that into some sort of context, right? Let me put it in, you're confused, man. Let me put it in some sort of context, right? Okay. You know when you're driving your car, you got a car? No. No, okay. Have you ever been in a car? Yes, come on, yes. You know when you drive around, right? And you see, you're going in your car up a mountain, and you see, steep gradient, 10% or something, 15% next 7 Ks or something, 20%, something like that. This is actually how they calculate it, okay? Actually, technically speaking, it's called the gradability of a road, okay? And when car companies manufacture cars, they have to think about, okay, what's the maximum gradient that this vehicle is designed to handle, okay? So those sort of ideas relate back to the gradient and this angle of inclination. Yes?
Just out of interest, where does the U have to go if it's 10?
Oh, it's got length 1, right?
Oh, okay.
So yeah, because it's a unit vector. You with me? It's a good question. Okay, so gradability. All right, so let's check our understanding. Some of these are straightforward, some of them are not. The gradient is a real big part of this section. You need to understand it, okay? Okay, so I'm going to ask you guys. Suppose we have grad f, where f's just some function of 2 variables. True or false? The expression grad f is well defined. Who thinks it's true? Who thinks it's false? Okay, why do you think it's true? Ah, who said it was false? Why? Yeah, absolutely. So this, f's just a real valued function, right? But as soon as you take the gradient, you form a vector. So how do you take the gradient of a vector? It's not defined, okay? So this is one of the important things where you need to distinguish and really understand when have I got a vector and when have I got a real value or a scalar, okay? So this is false. This doesn't make sense. This doesn't make sense at all. Okay, true or false? The expression f nabla is well defined. Who thinks it's true? Who thinks it's false? Okay, it's true. It's true. Why? Well, it's just scalar. So right, apply through by f, it's just scalar multiplication. True. All right. True or false? There is a function of 2 variables such that grad f equals positive 5. Who thinks it's true? Who thinks it's false? Why? Right, 5's not a vector. It's a scalar. It's a real number. So, false. Express df dx in terms of doof for some unit vector. Ah, well, we know that this is a special case of this for what you had. Anyone know? What vector is the directional derivative the same as df dx? Anyone? Well, I, that's it. Now, I'll let you check the details for that, okay? You can just prove, it's easy to prove. Okay, if we consider grad f to be some sort of derivative, then what's the opposite equation, opposite operation that cancels the grad f? Because, you know, I guess in regular calculus we have a derivative. What cancels a derivative? Integral, right? So if grad f is sort of a derivative, what cancels a grad f? Well, that's very hard, actually. I'll leave that one for now. I'll leave this one for you to do as an independent exercise. What do I mean by this? I mean, is that true? Can I have a show of hands? Who thinks it? Just have a guess if you don't know. Who thinks it's true? Why? Yeah, and what sort of technique might we use to differentiate this? What sort of techniques do we know? Yeah. So I'm going to say it's true. Okay? Yeah. So have a go at the two that I've left and see if you can work it out. But can you see how it's quite important to understand when am I dealing with a vector, when am I dealing with a scalar? When am I producing a vector? When am I producing a scalar? Okay, so if you can answer all these questions, you're doing pretty well.